Years at the MIB, or staff from all. There's also different academic schools within the university. And the program we put together are really challenge-led sort of research programs where we really try to stitch together all the different levels of expertise to address some of the key societal challenges in the sustainability space. So that's the MIB we've done for 10 years. We have increasingly focused over the years, so we're now very much driving I would say 100%, but most of us are very engaged in some way with the new emerging technology of synthetic biology, and using that as a key enabling technology to drive the sustainable synthesis of chemicals, materials, fuels, and other such products which are often sourced from petrochemical-based origins. And this is part of the transition to a more green economy. We set ourselves 3 major grand challenges. You may be aware, we just arrived on Beacon here at the university, and that really is very much focused on developing sustainable solutions to industrial chemicals manufacturing, particularly in Manchester, but also biopharmaceuticals and food security. We have other grand challenges in the fields of the areas of energy and fuels, and also a strong theme in biotech and healthcare. So all these are loosely referred to in the popular press as white biotechnology, green biotechnology, red biotechnology, parenthetically industrial biotech, nuclear biotech, pharmaceutical, medicinal biotech. So that's the buzzwords out of the way, and that's a history really of where the MIB has gone in the 10 years since it opened in 2005, 2006. Now, to bring all these sort of skills together for the different schools, we've also set up centres of excellence, which are often interface with industry as well. So it's not just academic work that we do, it's working with our industry partners. So we have an industry-focused centre working with bioanalysis, biotransformations, and other centres here as well, and networks that are working closely with industrial partners. And the recent centre that was established is one called SynBio, dreadful term, but it's there to reflect what we're doing in this new enabling technology of synthetic biology, which is the engineering of biology to do useful things for whatever application that may be. And to start, I want to talk a little bit about today, to give you a quite high-level view of the type of things we can do in synthetic biology to address the sustainability agenda. One thing I said at the Personal Chapter a number of years ago was that we can do something useful in the fuel engineering. We use biology to source a molecule that doesn't normally exist in biology. So the case of Bio-propane, which is currently derived, of course, from chemical feedstocks, can be designed a biological system that will enable us to make propane gas as a means of then fermenting, for example, bacteria or waste feedstocks, and there could be a whole range of different feedstocks. And in headspace of fermentation, can we generate propane gas which we can then take off and use as fuel. That was the grand challenge we set ourselves, and really to do that, we had to tackle, and are still tackling, a number of technological developments. First question is, why propane? Well, for obvious reasons, in the sense that energy supply and demand is always going up. It's a clearly pressure on lower carbon footprint. And just by way of illustration, biodiesel sales in the US to try and address some of these issues grew from 90 to 50 million tonnes in that period, 2004 to 2014. There's of course also legislation now about transitioning away from petrochemicals and also obviously from diesel and of course European directives to get I think 10% of biofuel requirements in transport fuels, and a UK commitment, as we stand at least today, to reduce carbon emissions by 2050. So these are the sort of political drivers, I think, to why we do this work. Commercial is already happening in that there is marketed now, say, marketed commercial process for bio-propane production by SHV Energy from Canada. It's not actually biological propane, this is taking the waste from the biodiesel production facilities around the world, and there's a thermal thermodynamic chemical process that will reduce the glycerol that comes from those production plants that chemically transforms glycerol into rather dirty propane, which is at least marketable as biopropane. Whether that's sustainable is how the crushing of the releases how it's marketed. So we were interested in trying to come up with a genuine fermentative approach that doesn't require sort of chemical treatment and what have you. Again, reminder that propane and of course butane comes from petrochemical sources. At the moment, there's a lot of this sort of activity going on where we're taking crops, oil crops, for example, drying the seeds, extracting from them crude vegetable oils, refining those vegetable oils, and food process purification. We can generate lots of biodiesel. That's happening all around the factory road. One of the major products that come out of that is this one here, glycerol from glycerin. And that's a major problem for the biodiesel manufacturing industry. What do we do with that dirty glycerol? There's no real good use of it at the moment. But we can grow bacteria with this, and that was the starting point for what we used to waste feedstock we could use perhaps, and think about turning that waste glycerin or glycerol into biopropane. So, here's some more drivers for why we wanted to ferment to microbial way of making biopropane. Then clean products from a whole array of waste feedstocks, so zero cost feedstocks, such as some using that will require value, so it will be zero cost, zero cost. It does offset the land use from biomass generated for other forms of biofuels. Much of it is a competition with biomass that's farmed across the globe. If you can get local distributed manufacturing, then there's energy security gains as well. So if you can set up a fermentation plant wherever you want to do them, to generate fuel, then there's no dependence on transport, of course. There's a massive gain in terms of security. Gaseous fuels can be separated from products quite easily. It's a gas, so you just take off the headspace. There's no problem here with toxicity to biology. You can make a product, you can separate from fermentation, and away you go. You've got a product that you can keep using. So this is the salt propane. There's already infrastructure in there on the petrochemical industry. We can transport propane quite easily. We can move it around. There's an infrastructure in place for its use as well. In fact, it's the third most widely used motor fuel, 20 million tons per year at the moment. It's also a more domestic fuel, providing heat energy for more than 40 million homes worldwide. So an existing global market. And as I say, it's very used to separate through liquefaction and so on and so forth. So it's a really good target. We could develop a sustainable method using biology to make this fuel. It would be, in my view, a transformative development. So how do we do it? Well, we thought about this a number of years ago. We thought of all sorts of biological routes to thinking about propane. None of these pathways exist in nature, so we have to engineer them from scratch. We think of starting as a proof of concept, something like glucose, which is a standard bacterial feedstock, very expensive, so not very user-friendly, but at least you can start with that as a proof of concept. In biology, you can draw on maps to connect all these different compounds, and you can begin to find enzymes from different bacteria, different organisms, splice it together, and come up with completely new metabolic pathways, which is what we've done. And this is, for example, the Cyanobacterial enzyme, and this is a very unusual enzyme. Just not only does you actually force it to do it, just finds on the sequence. So the first protein pathways that we see there from glucose are very useful, but glucose is very expensive. But at least it's a proof of concept. We do set out to think about, well, we know that microbes, for example, can make other molecules like butanol. We can piggyback on the back of that to try and make propane. Butanol is C4 alcohol. If you get yourself a butyraldehyde, which is a precursor, you take CHO off and then you get propane gas. So can we use that as a way into the biology? So we designed on desktop, all pathways, these are 4 pathways, and then we looked to populate those pathways with enzymes that we can source from different organisms, and we then get the genes of those and splice them together using synthetic biology approaches. And we can have a whole array of different metabolic sequences. Some of them are shown here. You can go this way, or you can go that way. There's a variety of ways around to find the problems down here at the bottom. And the prefix in here, asparagales, right into the central part of the metabolic map of any organism. So if we can tap into that, then we have a route to propane from a whole variety of feedstocks. So that was our design template. We went about looking for enzymes. Do that. The real challenge was finding an enzyme that did chemistry last reaction in the pathway. There is no enzyme that makes propane in biology. But there are enzymes in cyanobacteria that take this compound, into the details, except these are very long, floppy molecules, many carbon atoms, and they convert these through to this group here, this aldehyde group, which we can then cleave with this position to inform the component of an alkane or a alkane. So the chemistry is what we want to do, but the reaction itself is the wrong reaction. We need this to work a little shorter molecule. So how do we do that? 3 years ago we looked at enzyme, we known about it. The starting point is to first of all get the enzyme pure, crystallize it, sort its extract structure, and learn at the molecular level how it works. This is the reaction here. Taking off this terminal group here to form an alkane molecule, which in itself could be a very important fuel releasing chlorine. So we did the crystal structure, and we even did the crystal structure in the presence of the substrate, which is this long molecule here. But once we had that, we had to, again, design template to sort of say, well, okay, we don't want this to work in a long molecule here, but can we think of how to modify the structure of this protein genetically so that we can block off the other region of this pathway and restrict the short in carbon 4 substrates, which if you then knock off the peroxidable with the propane gas. So that was the approach. We made a whole series of variants of that protein. Some modeling here to show you how we did it. Logging off this access channel to restrict into a small molecule here. We put lots of different reactive groups into the protein using protein engineering. When we do that, then in presto we end up with variants of the enzyme now which have much higher activity with shorter chain substrates than the longer chain. So we've actually re-engineered, if you like, the specificity of the enzyme to work with shorter chain aldehyde groups, carbon 4 groups in particular, which is the substrate we need to generate propane. We also need butane by particularly C5 groups and decarboxylated C5. So now for the first time have a part, a biological part you can plug into a pathway and you can make propane gas. And just to show that we can do that, we take the enzyme, we put it into a microbial strain, we challenge it to work on a C4 substrate butane, and you can see that the engineered substrate now churns out propane gas for the first time in biology. So we have an enzyme that does that. We can go a step further, we can now construct our whole metabolic pathway for conceptual metabolism, and we can plug our enzyme in here. We can make a whole metabolic sequence that runs from this compound acid gray, this way, and we can look to see whether a living organism can use that new bioparticle to make a propane gas. It's a big gas, but it works. So it is. Here's a bunch of different controls. The key thing is this one here. This is the propane release locator. On this, it's moved out to a meter of focus of blowers. We need to optimize the process, but the proof of concept is there. That we can grow E. coli, the laboratory study of E. coli, with this whole engineered de novo metabolic pathways, and we can work glucose to make propane gas and collect that in the headspace of the organism. So that's first, and it's a starting point rather than an end point, but it really gives us the opportunity now to optimize that process and develop further. One of the problems with biology, if you look perhaps at the chemistry, is if you go from a feedstock to a product here, it's not a linear pipeline. This is a hose rather than a constant. Metabolic path is three-dimensional, four-dimensional. So intermediates in that pathway will have a point go into the rest of the tables, we will lose that part. So it's not the whole feedstock here, you don't end up with the whole gas here. Most of the escapes. So we've also got to engineer the organisms to block off these competing pathways, and that's quite a challenge as well. We can do it using new synthetic biology approaches. We've got CRISPR-Cas9 technology. We can do that. We can knock out competing genes, for example, butanol. And again, as we do that, we'll factor more propane gas to block off those excellent forms. So we have the technology now to keep doing this in an iterative way, where we can design, redesign, optimize, test, and get a better enzyme at the end. All this is in a laboratory, a little microbial, microliters, so it's not very useful. So we need to scale it, 500 scale, beautifully. And more recently, we've been able to set up a spin-out company, C3 Biotechnology is developing this research spin-out. There are parallel research platforms that we're developing C3 to optimize this process, as well as trying to get the first demonstration used out there on the broader arena. So I think there really is a prospect of scalable, sustainable, cost-effective use of propane gas, which can interface with a variety of different feedstocks. The beauty is that propane infrastructure is already there, so it's a real drop in fuel. If we can make a biosource or bio production process or provide propane, we can just drop into the existing infrastructure and propane gas that already exists. It's carbon efficient. It's very useful to footprint. So it all sounds, at least in my mind, that this is worth pursuing. Looking forward to try and address the political drivers that will be presented trying to get a view of global representatives. So that's probably where I leave it, gives you a flavour for where we're going, and so I can do the MIB. Okay? Thank you.